Nobody told you what was really found. That is the first thing you need to understand before we go any further. When the James Webb Space Telescope locked its golden eye onto Pluto, a world so far from our sun that sunlight takes over 5 hours just to reach it, the scientists operating the most powerful observatory ever built by human hands were not expecting what came back. They were not prepared for a signal that matched nothing in any database, nothing in any laboratory, nothing cataloged from any planet, any moon, any exoplanet ever observed across the entire known universe. And yet, there it was, a fingerprint in the light, a chemical whisper from the frozen edge of our solar system, something sitting on the surface of Pluto that humanity has never encountered before, not in a textbook, not in a simulation, not anywhere. The question is not what James Webb found on Pluto. The real question, the one nobody in the mainstream is asking loudly enough, is what it means for everything we thought we knew about where we live, what our solar system is, and what might be waiting out there in the dark. Let's start with the machine itself, because without understanding what James Webb actually is, you cannot appreciate the magnitude of what just happened. For decades, humanity pointed telescopes at the sky and got answers that were good enough. Hubble was revolutionary. It changed astronomy. But Hubble had a fundamental limitation. It could not see the universe in the way the universe most wanted to be seen. Infrared light, the thermal glow emitted by cold objects, chemical signatures locked in the mid-infrared spectrum. Hubble was essentially blind to all of it. So for years, entire categories of scientific truth were sitting just beyond our reach, hidden behind a wall of wavelengths we simply lacked the instruments to penetrate. James Webb changed that. Launched on Christmas Day 2021 with a 6.5-meter gold-plated mirror composed of 18 hexagonal segments, cooled to a temperature of negative 233 degrees Celsius, just 40 degrees above absolute zero, Webb was engineered specifically to see what no instrument had ever seen before. It was not just a bigger telescope. It was a fundamentally different kind of eye. And when that eye turned toward Pluto, toward a world that most people dismissed as a demoted dwarf planet at the cold, forgotten edge of the solar system, everything changed. But here is where it gets interesting, because Webb did not look at Pluto once. It has now looked multiple times, across multiple instruments, across multiple years. And with each pass, what came back was stranger than the last. The story actually begins not in 2026, but in 2015. That year, NASA's New Horizons spacecraft completed a journey of 9.5 years and nearly 5 billion kilometers to fly past Pluto at a distance of just 2,500 kilometers, closer than any human-made object had ever come to that frozen world. What New Horizons sent back shattered every assumption the scientific community had built. Scientists expected a geologically dead rock. What they found was a world that was, in every meaningful sense, alive. Nitrogen glaciers actively flowing across the surface. A heart-shaped basin of frozen carbon monoxide the size of Texas and Oklahoma combined. Mountain ranges rising 3 kilometers into the Plutonian sky. And above all of it, a blue haze, layered, complex, haunting. A photochemical smog stretching hundreds of kilometers into Pluto's thin atmosphere, glowing faintly blue against the blackness of space. Nobody could fully explain it. They knew the haze was there. They could photograph it. But the physics behind it, the mechanics, the thermal behavior, the actual role it was playing in Pluto's climate, remained frustratingly out of reach. And the reason was simple. New Horizons was a flyby. It zipped past Pluto in a matter of hours and kept going. It had no time to linger, no ability to study Pluto in the mid-infrared spectrum, no way to separate the thermal emissions of Pluto from the thermal emissions of its largest moon, Charon, which orbits so close that their signals blurred together into an indistinguishable mess. For years, scientists could only theorize. And one of the most consequential theories came in 2017. A planetary scientist named Xi Zhang at the University of California, Santa Cruz published a paper with a bold claim. He argued that Pluto's atmospheric haze was not just a visual curiosity. He proposed that it was the primary engine of the entire Plutonian climate system, that it was actively cooling the planet, shaping the distribution of volatile ices across the surface, and radiating energy back into space in a very specific and detectable way. His models predicted that if this were true, Pluto should be emitting a distinct and measurable thermal signal in the mid-infrared range. But in 2017, there was no instrument on Earth or an orbit capable of detecting it. So Xi Zhang's hypothesis sat in the literature, unproven, waiting for a machine that did not yet exist. That machine was James Webb. And when Webb finally turned its mid-infrared instrument, known as MIRI, toward Pluto, what it saw stopped the scientific community cold. Not because the prediction was wrong, because the prediction was exactly right. Webb confirmed, for the first time in history, that Pluto's haze is radiating measurable thermal energy into space at 15, 18, 21, and 25 micrometers simultaneously. The haze is real, it is active, and it is in charge. As Shijong himself said, with barely concealed astonishment, it is rare in planetary science to have a hypothesis confirmed so quickly, within just a few years. They felt lucky. They felt excited. But that was only the beginning of what Webb was pulling out of the dark. Think about what this discovery actually means. Pluto sits 5.9 billion kilometers from the Sun at its farthest point. It receives roughly 900 times less sunlight per square meter than Earth does. By every conventional model, it should be a passive, frozen, geologically inert object, a relic of the early solar system preserved in cold storage. Instead, what Webb is revealing is a world with an active climate system. A world where atmospheric haze behaves not as a passive byproduct of chemistry, but as a thermostat, simultaneously cooling Pluto's surface while energizing atmospheric molecules to escape into space, actively regulating the planet's energy balance in a way that nobody predicted and nobody fully understood until now. This is not a frozen rock. This is a dynamic world with its own rules, and those rules, it turns out, may not be unique to Pluto. This is where the implications begin to scale beyond a single distant world. According to researchers involved in the Webb studies, Pluto's haze-dominated climate bears a striking resemblance to the atmospheric behavior of Titan, Saturn's largest moon, a world so complex that some scientists consider it a candidate for primitive life, and Triton, Neptune's moon. What Webb is suggesting is that haze-controlled climates may be a category, not an anomaly. That across the outer solar system, worlds too cold and too distant to be powered by traditional sunlight may instead be regulated by photochemical hazes, operating in ways we are only now beginning to map. And then, Webb found something else, something far harder to explain. On June 11, 2026, a team of researchers uploaded a study to the preprint server Arkref, in which they described analyzing James Webb observations of Pluto and Titan while focusing on infrared wavelengths that had remained relatively unexplored. During that analysis, they detected a distinct absorption line, a gap in the spectrum where light is being absorbed rather than reflected, centered at precisely 511 micrometers in the spectra of both worlds. An absorption line is, in the simplest terms, a chemical fingerprint. When light hits a surface, different molecules absorb different wavelengths. By reading which wavelengths are missing from reflected light, scientists can identify what substances are present. It is one of the most reliable tools in all of astrophysics. And what James Webb found at 511 micrometers on Pluto does not belong to any substance that science has ever cataloged. Read that again. The researchers cross-checked the signal against every known planetary spectrum in the scientific literature. They reported that they did not find any band referenced in these publications that corresponds to the location of the observed absorption in Titan and Pluto. The detected signal does not match any known chemical compound identified elsewhere in the solar system or on observed exoplanets. Not methane, not nitrogen, not carbon dioxide, not water ice, not ammonia, not any of the complex organic molecules that astrochemists have spent decades cataloging across the solar system. Not anything. Something is sitting on the surface of Pluto, and possibly on Titan as well, and science has no name for it, no laboratory sample of it, no theoretical model that predicted it. But here is where it gets stranger still. The researchers are confident that the molecule responsible for the 5.11 micrometer absorption line is located on both worlds' surfaces, not in their atmospheres. That distinction is critical. If this were an atmospheric signature, you could explain it through chemistry happening in the upper layers of gas, ultraviolet radiation breaking molecules apart and reassembling them into new compounds. Atmospheric chemistry is wild and produces strange things, but this signal is coming from the surface, from material that has been deposited, accumulated, or formed directly on the frozen ground of Pluto, 4 billion kilometers from the Sun, in temperatures approaching negative 230 degrees Celsius. Whatever this substance is, it is not a transient atmospheric curiosity. It is sitting there. It has mass. It is part of Pluto's physical landscape in a way that demands explanation. And the details of the signal make the mystery deeper, not shallower. Pluto's absorption line is around 3 times thicker than Titan's, meaning the mystery molecule is likely much more abundant on the dwarf planet. 3 times more abundant, on a world that most textbooks described, until recently, as a geologically simple ball of ice and rock. Meanwhile, on Titan, the same signal is present but distributed unevenly, stronger on one hemisphere than the other, suggesting that whatever this molecule is, it is being formed or deposited through some process that interacts with the geometry of the moon's orbit or its exposure to Saturn's magnetosphere. The same substance, on 2 completely different worlds, behaving in subtly different ways, following patterns that no existing model predicted. This is not noise. This is not an instrument artifact. This is a discovery. What most people are not seeing is the architecture of what James Webb is doing here. This telescope is not just finding new things. It is dismantling old certainties. Every model of outer solar system chemistry that has been refined over decades assumed that scientists had a reasonably complete picture of what molecules could exist in these extreme cold environments. The assumption was that the chemistry out there was limited. Simple molecules, simple interactions, simple surfaces. Webb is proving that assumption wrong in real time. The outer solar system is not a chemical desert. It is a laboratory operating under conditions that we have never replicated on Earth, producing substances that our instruments until now could not even see. Let's talk about what this means for the question of life, because it would be dishonest to raise these discoveries without addressing the possibility directly. These discoveries open the possibility that life, in extreme or past forms, could have existed outside the classical habitable zone of the solar system. That is a measured, carefully worded statement from the scientific community. But unpack it, and the implications are staggering. The classical habitable zone, the so-called Goldilocks zone, is the region around a star where liquid water can exist on a planet's surface. Earth sits squarely inside it. Mars barely grazes the inner edge. Beyond that, according to traditional thinking, it gets too cold, too dark, too hostile for any chemistry associated with life to function. Pluto is not even close to the habitable zone. It is billions of kilometers beyond the outer edge of anything that conventional models would consider life-friendly. And yet, here is a world with an active climate. Here is a world with an unknown substance on its surface, something complex enough to produce a unique infrared fingerprint that matches nothing in the chemical inventory of the solar system. Here is a world whose atmosphere, as Webb has now shown, interacts with its surface in dynamic, seasonally shifting ways, depositing material from Pluto's thin air onto the surface of its own moon, Charon, in a process that is entirely unique in the known solar system. The data collected reveals significant variations in heat flux, highlighting the surface properties of the two bodies and the strong thermal emission of Pluto's haze, confirming that the haze plays a central role in regulating Pluto's climate, in a similar way to Titan's atmosphere. And Webb's observations of Charon itself have added another layer entirely to this unfolding story. When Webb pointed at Charon, Pluto's largest moon itself, a world about half the size of Pluto, orbiting so close that the two are tidally locked and face each other perpetually, it found things that no previous mission had the sensitivity to detect. Using the James Webb Space Telescope, astronomers discovered carbon dioxide and hydrogen peroxide at the surface of Charon, potentially shedding light on its origins. Carbon dioxide on Charon is itself surprising. It suggests that the moon's surface is preserving a chemical record of how it formed billions of years ago, when the outer solar system was a churning violence of collisions and chemical reactions. But hydrogen peroxide is something else entirely. Hydrogen peroxide forms when water ice is bombarded by ionizing radiation over geological timescales. Its presence on Charon tells scientists that the moon's surface is not static. It is being actively processed, irradiated, chemically transformed, even today in the frozen dark at the solar system's edge. And woven through all of this is a detail that makes the entire picture feel even more unsettling to contemplate. The material from Pluto's own atmosphere is being deposited on Charon's surface. Think about what that means. Pluto and Charon are so close, only about 19 to 600 kilometers apart, closer than many Earth satellites, that Pluto's thin atmosphere leaks across the void between them and rains down onto Charon's dark polar regions. Webb has now confirmed that this process is real, measurable, and ongoing. It creates what researchers have called a phenomenon unique in the solar system, a world actively painting its own moon with atmospheric material. And now, somewhere in that atmospheric material, somewhere in the chemistry raining down from Pluto onto Charon, there may be traces of this unknown molecule, this unnamed substance at 511 micrometers, spreading across two worlds simultaneously. The authority of what James Webb is producing cannot be overstated. This is not speculation from a ground-based telescope interpreting blurry pixels. Webb is operating at a sensitivity and resolution that separates Pluto's signal from Charon's signal, two objects separated by less than 20,000 kilometers when viewed from 5.9 billion kilometers away, and reads their individual chemical signatures at wavelengths that no instrument in history has accessed before. One major challenge was Pluto's large moon, Charon, which orbits so close that their thermal signals often overlap in telescope data. Webb's powerful infrared instruments were finally able to separate the two worlds' signals. When scientists say that what Webb found is unprecedented, they are not being dramatic. They are being precise. Now, step back from the chemistry for a moment and look at the broader geopolitical and scientific landscape this is reshaping. The outer solar system, the Kuiper Belt, the vast ring of icy bodies beyond Neptune in which Pluto orbits, contains thousands of objects. Some of them are enormous. Eris, another dwarf planet, is nearly the same size as Pluto. Make, Sedna. Haumea. None of them have ever been studied at this level of detail. What Webb is now demonstrating is that Pluto is not an exception. It is a sample. These discoveries suggest that other bodies in the Kuiper Belt could have similarly complex characteristics. If Pluto, which was studied up close by New Horizons and is arguably the best understood Kuiper Belt object, has an unknown molecule on its surface, an active climate system powered by its own atmospheric haze, and a chemical relationship with its moon that has no parallel anywhere else in the solar system, then the working assumption must be that the other thousands of objects in the Kuiper Belt are similarly complex, similarly surprising, and similarly misunderstood. The entire outer solar system just became more interesting and far less known. What most people are not seeing is how this changes the funding conversation, the mission planning conversation, and the scientific priority conversation happening right now in the corridors of space agencies around the world. The scientific community is already discussing the feasibility of sending an orbital mission to Pluto to study these phenomena more closely. Not a flyby, an orbiter, a spacecraft that would enter Pluto's gravity, map every inch of its surface at high resolution, sample its atmosphere, and potentially deploy surface probes. The cost of such a mission would be enormous. Preliminary estimates for a Pluto orbiter have ranged upward of $3 billion, and the travel time alone, even with optimized trajectories, would be measured in decades. And yet the conversation is happening, because what Webb is returning is making the scientific case in a language that cannot be ignored. The language of discovery after discovery after discovery, each one stranger than the last. The NASA Dragonfly mission, currently targeted for launch no earlier than 2028 and scheduled to arrive at Titan in 2034, carries a spectrograph specifically designed to directly sample surface materials. The spacecraft will carry a spectrograph capable of directly sampling surface materials, potentially identifying the same compound on Titan and clarifying whether it also exists on Pluto. That is 8 years from now. 8 years before humanity gets its next best chance to physically interrogate this mystery molecule at close range. And even then, Dragonfly is going to Titan, not Pluto. If the unknown substance at 511 micrometers proves to be something biologically relevant, a precursor molecule for amino acids, for instance, or a compound associated with the kind of chemistry that eventually gave rise to life on early Earth, then the mission to Pluto just became the most important space mission ever proposed, and we do not yet have one scheduled. Here's something that the mainstream coverage of these discoveries consistently fails to emphasize. Webb's findings on Pluto are not isolated, they are part of a pattern. Earlier in 2025, an international team led by researchers from CNRS and the Paris Observatory published findings in Nature Astronomy, one of the most prestigious scientific journals in the world, confirming Webb's detection of Pluto's haze thermal signature. The findings also hint that other worlds, including our own, may have a hazy history as well, potentially reshaping our understanding of how Earth came to possess its current climate. Let that sink in for a moment. Scientists studying a frozen dwarf planet at the outer edge of the solar system are now drawing lines of connection back to the early history of Earth's atmosphere. The suggestion, still preliminary, still being tested, is that the kind of haze-dominated chemistry Webb is observing on Pluto today may mirror what Earth's own atmosphere looked like billions of years ago in the early Archean eon, before oxygen took over and the chemistry of life began to dominate. If Pluto is a frozen record of ancient atmospheric chemistry, a kind of cryogenic time capsule, then understanding its haze is not just about understanding Pluto. It is about understanding where Earth came from. The real story is that humanity is in the middle of a renegotiation with the solar system. For generations, the working model was simple. Inner planets are rocky and warm. Outer planets are giant balls of gas. And beyond Neptune, there is a cold, quiet, largely empty wilderness of frozen debris left over from the formation of the solar system billions of years ago. The Kuiper Belt was an afterthought. Pluto was a footnote. Literally demoted from planetary status in 2006, stripped of its classification, reduced in textbooks to a rounding error of cosmic real estate. And then New Horizons flew past and showed us a world of heartbreaking complexity. And then James Webb started reading the light coming back from that world. And what it found is forcing a complete reassessment of what the outer solar system is, what it contains, and what it might mean for the deepest questions science can ask. There's an unknown molecule on the surface of Pluto right now. It has been there, accumulating, possibly spreading, possibly being formed continuously through some ongoing chemical process. And for the entire history of human civilization, we had no instrument capable of detecting it. That molecule is sitting there at 511 micrometers, absorbing a specific slice of infrared light, leaving its fingerprint in the spectrum, waiting to be identified. Scientists have checked every database they have, every laboratory compound, every known molecule observed on every planet, moon, asteroid, comet, and exoplanet that has ever been studied, and nothing matches. Whatever this thing is, it is new to science. And Pluto has 3 times more of it than Titan does.